All right, in this next few lessons, we're going to talk about related rates. And related rates is kind of like the meat and potatoes of derivatives. It's where everything comes together, and this is what a derivative does, okay? And this is the basis to larger problems that you're going to work in higher order math, okay? We're talking like big math, big boy math, and big girl math, and big architecture things or big engineering things. These are the baby word problems that lead to all of that. All right. And the best way to kind of go through these word problems is a couple steps. One, as you work through an example of a word problem, work through that word problem several times until you can get the right answer every time, and that you can set the problem up on your own every time. Sometimes setting the problem up on your own is the most difficult part. So um, work this first example through a couple times. Do you see where everything's coming from? Do you get it? Do you not? Are you sure? Are you unsure? There's some great internet resources. Just type in calculus related rates into either YouTube or Google, and you'll get a lot of different things. Because sometimes on this, you need to hear more than one person speak. Also, with related rates, there's like a little process you're going to have to go through on each one. Each problem is unique. I can't go, okay, on this problem we're going to do this, and then this, and then this. All these problems are just a little bit different, and that's what kind of makes them fun. They're like a little bit like puzzle pieces. You have to figure out what puzzle pieces you need and put them together in the right way to get a cool shape and fun puzzle. All right. The problem is it's a trick puzzle kit, and they give us a few extra pieces, so we have to figure out what to not use. All right. Um, for those of you in my class, your book gives you a strategy for solving related rates. You need to understand what the problem is. What are they asking you to find? Is it the area of a circle or a sphere or a cylinder? Is it the perimeter of a rectangle? Are they asking you to find distance? What are they asking you to find? Then figure out a mathematical model to relate all those things together. Again, it could be setting the area equal to a specific number that's listed in the problem, or who knows what. You're going to write out your equation that relates all of these different things together, and sometimes that might be two equations. You're going to write all those things out and find out what their relationship is. You're going to take the derivative of both sides of your equation. You're going to substitute any values that you were given as a starter value, like you started here, you stopped there. And then you're going to interpret what your solution is. And that's really a critical part. Let's say, for example, we're talking about cars that are chasing each other, and you get some sort of how fast is car B going, and you get 3,462 miles an hour. Guess what? You've probably got an error in your math. But if you do that same problem and you get something where car B is going 83.6 miles per hour, well, now you're onto something. So it's really important to kind of understand initially what that whole problem's asking you for. So this first guy is, a little softball to lob at you to see if you can get everything figured out and see what we're going to do. But critical thing here, create a problem, create a model, determine your equation, and differentiate or take derivative of both sides. Okay, so let's just start with what we've got. The radius of a sphere is a differentiable function of t, and allow v to be the volume of the sphere. Find an equation that relates change in volume with change in radius. And what does that mean? Change in volume would be something like the change in volume over the time. Okay. What about the change in radius? That would be something like dr dt, the change in radius over the change in time. These are the things that we're going to be interested in. So let's talk about this. We've got a sphere with a volume. So we know we're going to have some sort of volume situation developing here. So the volume. Now you may need to Google this, so if you need to, just pause and go do that. But what is the volume of a sphere? Like, what's the equation? And the equation is 4/3 pi r cubed. That's it. Now, how can I get dv and dt out? dv dt and dr dt? Well, remember, we're talking about a function over time, okay, f of t. And we're given this equation. We've got our equation here of volume and radius. Those are the only two variables. 4/3 pi is a constant. So what I can do is take the derivative of both sides. Now, when we do this, we would have v prime equals 3 times 4/3 pi r squared. That's your derivative, okay? Clean this guy up. You'll notice that the 3's divide out, and I'm left with v prime equals 4 pi r squared. Now, remember, since t was our original variable here, the thing, a differentiable function of t, we need to add behind the r a dr dt. Okay? It's pretty important to add that part. So we would just carry him down here, dr dt. Now, the cool thing is we're actually done with our problem at this point. Okay? We've taken a derivative of both sides. The weird thing is the left-hand side looks like v prime. The right-hand side has that dr dt in it. That's the relationship we're looking for. So what do? Well, we just keep in mind that v prime has a whole slew of different ways that it could look. V prime is the same thing as dv dt, which is the same thing as d. Let's see here. That's not it. V over dt. Or v prime of t. Like, all these different things are the same. And the one that we want is right here that compares volume and time. So we would just finish our problem off by saying dv dt is equal to 4 pi r squared dr dt, and that is the end of our problem on this particular case. That's all we needed to do. Find an equation that relates change in volume with change in radius. All right, let the radius be r and height be h of a cone, both differentiable functions of t. Let v be the volume of the cone. Find an equation that relates the rate of change of the volume with the rate of the change of the radius and rate of change of the height. What? All right, here's the deal. It's very similar to the very first example that we set up. We've got this differentiable function of t. So that means t is kind of our hidden guy in there. Even though we don't see him right off the bat when we take derivative, we're taking that derivative with respect to time. So we need to use the chain rule part of that. All right. So we want volume of a cone. Volume of a cone. Anybody remember that? Volume of a cone? I think it's something like this. Correct me if I'm wrong. I have been wrong on an occasion or two. So 1/3 pi r squared h, I believe, is the volume of a cone. Okay? And so how does this all work out then with what we're trying to do? Well, to clean us up just a little bit and give us a little bit easier look at it here, I'm going to go ahead and write pi r squared h over 3. Okay, that's the same thing. Would you agree with that? R squared and h are over 1, so is pi, so I could have this situation right here. Now, we want v to be the volume. We want to find an equation that relates the rate of change of volume, rate of change of radius, and rate of change of height. So if you'll notice right here, we're going to have a chain rule situation. Okay. What we want to do now is we've got the equation that we're going to work with. Okay. We've developed our mathematical model. We've got an equation that we're going to work with. Now we're going to take derivative, and we have to take derivative of both sides. So remember, like we talked about on that previous slide, we want dvda version or dvdt version of derivative. So dvdt is equal to, and then we want to take the derivative of this side. You know what? Maybe this one is easier to work from for derivative purposes. But also for derivative purposes, we have to chain rule that. So let's dive in, shall we? It's the first 1/3 pi. Okay, 1/3 pi r squared h, r squared, times the derivative of the second. So 1/3 pi r squared times derivative of the h, which is 1, then times dh dt. Why dh dt? Because we're looking at the change in the height over the change in the time. Okay, dh dt. Plus 1/3 pi times the derivative of the first, 2r, times dr dt. Why dr dt? Because we're looking at the change of the radius over the change in time. Okay, we have to have that. Times the second, which in this case is h. So your final answer, you don't want to leave it like that. That's a little bit yucky. We want to clean it up a little bit if we can. And now we can kind of go towards this form right here that I wrote at first. I've got pi r squared all in numerator. So dv dt would be pi r squared over 3 times dh dt. Plus, and on the other side, pi and 2r and h are all in the numerator. So I could have 2hr pi over 3 times dr dt. And that's your answer right there. That's an equation that relates change in volume with change in height and change in radius. And that's the question that we're asked to find. Something that relates all three of those together. All right, a police cruiser is approaching a right-angled intersection from the north, chasing a speeding car that has turned the corner, now moving straight east. When the cruiser is 6/10 of a mile north of the intersection, the car is 8/10 of a mile to the east. The police determine with radar the distance between them, and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So what we've got here is a situation where we've got a police car, and might help to draw this picture. So a police car is approaching a right-angled intersection from the north. So something thusly. The bad guys have turned the corner, and they're moving now straight east. So they're moving straight east. All right. And so here we've got the police right here. We'll give them a red car, you know. I don't know, blue, red, doesn't matter. So here's the police car. It's a dragster police car. And I'll give him some flashy lights here. All right, police car right there. And his lights are radiant and flashing. Okay, police car. Chasing the bad guy's car. So bad guys are this way. And let's see what kind of car they're going to have here. What am I going to draw? A speed racer car. Nope. A speed racer tractor car. Wow, I'm a terrible artist. Okay, so here's the situation we've got. Police cars coming into the intersection this way. Bad guys leaving the intersection this way. And we're told that the cruiser is 6/10 of a mile north of the intersection. So this is giving us some information here. So basically what we're doing is we're setting up our model. So they're 6/10 north. Bad guys are 8/10 east. Okay. The police determine with radar the distance between them and the car is increasing at 20 miles per hour. Okay. So that's giving us a rate. Did you catch that in there? The speed is changing is decreasing at 20 miles per hour. Okay. So if we call bad guy X, if we call police Y, because it's kind of the directions they're moving, then let's call the distance between the cars. So that's another thing here. Distance between, let's pick a fun color, orange. So at this exact instant in time, here's the distance between our cars. And we're going to say that that is changing at 20 miles per hour. So let's call that guy Z. All right. So the change in Z with respect to time at this instant is 20 miles per hour. Okay. All right. Now, a couple things. Since the police car is moving down towards Y, then let's go ahead and give him a negative rate of change. Okay, we'll say, so we would say that this is the origin right here. So we're not moving away from the, we're not moving up away from the origin, we're moving down towards the origin, towards negative numbers. So the rate of change of the police car is 60 miles per hour. The cruiser's moving at 60 miles per hour. That's a rate of change. So dy dt is equal to 60 miles per hour. All right, so we know that, and since he's going in a negative direction, we're going to say that he's negative. We've got the rate of change between the police car and the bad guys here is 20 miles per hour. Looky here, we've got us a Pythagorean triangle, and I feel like this is going to be important, so I'm going to go ahead and note it. All right, Pythagorean triangle. So if the cruiser's moving at 60 miles per hour at the instant of measurement, what is the speed of the car? In other words, what we want to know is the change of rate of the car, the speed of the car. What is dx dt? So let's think about this. What equation do we have an idea of that maybe possibly relates these things together? This side z up here, this side x, this side y. I'm thinking it's a Pythagorean relation. Something along the lines of what good old Pythagoras shared with us several thousand years ago. Something he either discovered or borrowed and became famous for. At any rate, it's x squared plus y squared equals z squared. I think this is going to be the equation that relates all three of these variables that I've drawn out here together. Okay, so what do we need? Well, I've got change of rate of the police car, change of rate of the distance between the car and the bad guys. I need change of rate of bad guys, which means that I've got to take derivative of this. So let's do it. I'm going to have 2x times dx dt. Why? I have to have dx dt. I have to have dx dt because I'm talking about the rate of change with respect to time. So I've got to have that in there as part of my derivative. 2y dy dt, again, same reason, rate of change with the y car in respect to time in the y position, and then 2z dz dt. Y dz dt, that's the rate of change of the distance between the cars. Well, it's all over but the crying now. I just need to figure out and solve for and eliminate and discover and find out and do some math and scratch and calculate and squirm, and I'm shooting for that guy right there. The problem is I've got x dx dt, y dy dt, z dz dt. Well, looky here. I've got x, I've got y. I don't have z, but can I find it? And the answer is yes. So what I'm going to do is I'm just going to run Pythagorean's theorem. 0.6 squared plus 0.8 squared square rooted will give me z. Now my calculator's gone missing, so I'm going to trust our text here because, well, they haven't been wrong yet, frankly, and according to them, I get a grand total of, looks like 21. It's going to be 1. So this is a 1 right here. So what is that going to look like? Well, I plug z in here for z. I plug dz dt in here. With my y's, I plug my y value in, which is the police values. My y value goes here. Speed of the police car goes here. The x value of the bad guy goes here. Speed of the bad guy there. That's what we're trying to find. So what turns out is I've got everything except dx dt. So I'm going to go ahead and substitute all of that in now. So I'm going to have 2 times 0.8 plus times dx dt plus 2 times 0.6 times dy dt. And then over here I'm going to have 2 times 1 times 20 miles per hour. And right here, instead of dy dt, I know how fast the police are going. Police are going -60. Alright, so I'm going to throw all this into my calculator. I'm going to squeeze it all down, and what I should end up with is that dx dt, the rate of change of the bad guys, is going to turn out to be 70 miles per hour. How did I get that? Well, I did this math right here. Again, I don't have my calculator with me. There's going to be some maybe decimal action, but this is going to be 1.6 dx dt equals 60 times 2. 60 times 2 is 120, so this would be 120 times 0.6. All I did was move it over, plus 40. So there you go. Simplify that real quick, and you've got your answer. Okay. That's it. That's a related rate. What did I need? I need a Pythagorean theorem and a derivative. So with all of this stuff that you're going to do, a derivative, he's right there with you the whole time. He's not going away. You need to make sure that you figure out an equation that does that. And also with almost every single one of these, we're talking about time. So when you take your derivative, you're going to have to chain out that dx dt part, dy dt, whatever your variable is, over time, so that you can account for that, because we are looking for a rate of change. Okay, here's a fun one. The old conical tank, because everybody's got one of those in their backyard, right? I don't know. I did it when I was a calculus student. I think it's a calculus student rite of passage, the draining conical tank question. All right? Now it's your turn to learn how to find how quickly the water is rushing out of a conical tank, or how quickly the height is changing, or some sort of conical tank question. They're everywhere in calculus. So, water runs into a conical tank at the rate of 9 feet cubed per minute. Sounds like a change in volume. The tank stands point down and has a height of 10 feet and a base radius of 5. How fast is the water level rising when the water is 6 feet deep? All right, picture time. And if anything, even if we don't understand everything we just read, we can at least understand enough to draw the picture. So here's my conical tank. Okay, and water is running into the conical tank. So we've got water in here somewhere. Okay, water, water, water. All right, water's running into the conical tank. Some other things that we know. We know that the change in the volume over time is 9 feet cubed per minute. Okay, we know that for a fact. We also know that the tank has a height of 10 feet. Okay, and it has a base radius of 5 feet. Okay, in other words, the radius where our base would be right here is 5 feet. The 10 would be this part right here. Okay. So here's our information. We know that we're working with a cone, so we need volume of a cone because we're looking at change of volume. So the volume of a cone is equal to, is it 1/3 pi r squared h? I'm just going to double check it is. All right, so how fast is the water level rising when the water is 6 feet deep? So I'm going to go and change now to blue. So we are looking now for this triangle right here. All right. The question for us is dH dt. What is dH dt when h is equal to 6 feet? So what to do? Well, you might notice, or you might not have noticed, that we've got a situation here where we've got a similar triangle action shaping up. Here's a big triangle in pink. There's a little triangle in blue. They're similar triangles. So what we could do is we could look at the ratio then, the ratio of the radius to the height, which would be 5 to 10. All right. The other ratio then that we would be interested in is going to be this little guy right here, and we know when we're looking at that it's going to be 6 to whatever, I don't know, and it might not even really matter, but it's got to have the same ratio right here in blue as my guy does in pink. Okay, so let's just look at radius and height right here. I've got radius and height right there. Maybe if I can eliminate one of those variables, hey, I know height is 6 feet. Maybe if I could rewrite this thing with an R, all R's, maybe that could help me out somehow. So here's what I'm going to do. I'm going to multiply both sides down here in this equation by h. And I'm going to reduce it down, and I'm going to have R is equal to 1/2 h, okay, or h over 2. So I can come back here to my volume, and that was all similar triangle work there. Nothing fancy, no trick up my sleeve, times, and then, whoops, I wrote out r squared. What is r? R is this guy, h over 2 squared times h. Remember, 1/2 times h is the same thing as h over 2. So look now, I have an equation without an r in it, so I don't have to chase around a ton of different things. I don't need the rate of change of the radius. I just need rate of change of height. So even though I know when my height is 6 feet, I'm going to need that eventually, okay? But I don't need it right off the bat. So now let's look at the derivative of this, dv dt. And 1/3 pi is a constant. And let me just move this guy down just a slight skosh. Let's have a rewrite. So here we've got v equals, now h squared times h, that's h cubed. Learned that a long time ago. So h cubed over 2. So h cubed 1/3 pi times h cubed over 2, and that would be 1/6 pi h cubed. All right. Whoops, that should be a 4. Dadgum. This is 4 because it's h squared, and h is h over 2. So this 6 is actually a 12. There we go. There we go. I think we are ready to proceed. All right, so I've got pi over 12 times h cubed. Derivative time, so that's going to be 3 over 12 or 1/4, 3 over 12 or 1/4 h squared times the change in h over the change in time. Okay, that doesn't look too bad at all. It's, in fact, feels like something I can work with. Why? Because I've got that height that we're interested in right here. I've got a change in volume right here. And so the only thing that leaves me with that I need to find that's a critical thing is the change in the height. And hey, that's what our question in this case is. So I'm just going to rewrite everything here. I'm going to substitute in all the goodies. So I'm going to have 9 equals 1/4 times 6 squared dH dt. Do not put the fraction together first. This is 36 over 4. Okay? That's 36 over 4. Oh, there should be a pi. Where'd my pi go? Right here. Oh, those are different colors. Yikes. Pi right here. Pi right here. All right. Times dH dt. Now, an exact answer here for me. An exact answer here for me would be, well, 36 over 4 is 9. So let me see if I can wrap this up in one more step. 9 pi dH dt. Divide both sides by 9 pi. So that's going to end up with 1 over pi equals dH dt. Okay, here's the deal. I don't really know what 1 over pi is. And we're talking about rate of change. So I need something a little bit more hand graspable, understandable item of thing. 1 over pi is perfect, exact answer. Totally 100% exact and correct. But give me something I can work with here. So go ahead and punch 1 over pi into your calculator, and you're going to get that that's going to be 0.32. 0.32 what? Okay. Well, we're talking about how fast the water is rising, and we've been talking about everything with feet and minutes. So it's changing at 0.32 feet per min. And I don't know if you're going to be able to see all that on there, but the correct units on that puppy is feet per minute. And there you go. There's the old cone related rate problem. It's a dandy. It's a dandy, and it's one you always get to do in calculus. And one of these days when your kids take calculus, you can go, "Yep, I did the conical problem too, and survived it." So words of encouragement. And again, practice this problem. Cover up what you just did right now. Just cover it up. Read the problem again. Read the words. And see if you can't reproduce everything that was written here. There's another way that you could solve this out and get the same answer too. It also requires you to pay attention to this relationship right here, okay? The R over H and the 5 over 10. So see if you can work this problem out and get the exact same thing. And if you can't, come back, watch the video, get a little help, cover it up, and try again. All right, here's a fun one. A man 6 feet tall walks at a rate of 5 feet per second towards a street light that is 16 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? So what we're going to have is some sort of street lamp issue thing, public safety deal, and he's casting a shadow this way. So here's the street light. It looks like the sun, so we'll make it more lamp style-ish. There we go, lamp. Fun lamp shape. And this lamp is casting a shadow. Now, I'm going to use some of my tools that are given to me here. But remember, from a lamp, you're going to get a straight line shadow. Light travels in straight lines. Now, inside this line, we've got a guy walking. And here's, whoops, we don't want that right there. Let's just undo that, go to this. Okay, we've got this dude walking, and maybe, it's the festive winter holiday season. Maybe this dude is none other than Santa Claus. Okay, here he is, Santa Claus, big Santa Claus, fun hat, a little cool hat thing. Looks like, wow, that's really bad. Let me try again. I can do better. I can do better. Be patient. Be patient. A little ball deal up there. It's all red, and he's got a snowy white beard. So here's his beard here, and a couple of Santa arms. And wow, I am not an artist, so I'm sorry. some green gloves because hey, it's Christmas time, festive winter holiday time. Wow, I am so bad. Okay, so here he is, Saint Nick, and he's walking with his cool black boots and his little. Here we go. Here we go. He's coming together. He's coming together. Black boots, and he's walking towards the light. Don't go into the light, Santa. No, no, not into the light. Okay, just kidding. So Santa's walking towards the light, and he's walking at his shadow's changing. All this stuff's happening. Some nerd somewhere determined that Santa was exactly 6 feet tall. Now, I don't know if that's in a story somewhere and I missed it, but Santa's 6 feet tall. The lamp post here is 16 feet tall. So the question is, if Santa's walking towards the light at 5 feet per second, how fast is his shadow changing? And the question is, I don't know, but can we find out? And the answer is yes, we can. Check it out. We've got a couple of triangles here. Again, here's this big triangle. Let's call it this one right here. See the big triangle right here? Horribly outlined. Okay. And then inside it, we've got this other like bluish triangle here. See this triangle right here? There you go. Those are the two triangles that we're interested in. So let's label some stuff. I always like to label up and down Y, and we got to break Santa Claus up into a couple things. One, we got to break Santa Claus up into the distance he is from the lamppost, and then the distance for how long his shadow is. So let's call the distance between Santa and the lamppost X, and the distance from Santa to the tip of his shadow Z. And we know that he is 10 feet from the base of the light. So we know that X is going to be equal to 10 feet. Z we don't know. Now here's the other thing. A couple other things that are really key that we need to notice. One, the rate of change of Santa Claus as he's walking. He's walking towards the origin. That's a negative number. So he's walking at negative 5 feet per second. The other thing that's interesting to note, and we may or may not need this, I don't know. The lamppost height never changes. And if something doesn't change, it has no rate of change. Now, this might come in handy if we need Pythagorean theorem, but I'm just going to say, you know what? dy dt, that's 0. It's not changing. And guess what? Santa Claus isn't growing either. So there's no way for Santa Claus to change and grow taller, so dy dt is 0 all over the place. All right. Well, I'm thinking some similar triangles are what we're going to have to look at here. And so if I look at that little blue triangle, I'm looking at side Z over Santa Claus, which is a base of 6. And on that bigger triangle, I'm looking at an X plus Z, that side, X plus Z over the height of the lamp, which is 16. So when I work this out, I get 16z equals 6x plus 6z. And I'm going to go ahead and move over my z's, and that's going to give me my 10z equals 6x. Now, go ahead and leave them like this. You don't necessarily need to completely solve for one variable or the other, or you might want to. I mean, it doesn't matter. But the thing we're really interested in, okay, after we have all of our setup done, is at what rate is the shadow changing? At what rate is the shadow changing? Remember, shadow is z. So dz dt is really what we're interested in. So I've drawn a picture. I've established a model. I've given myself an equation. Now I'm going to take derivative on both sides. So 10 dz dt. Why dz dt? Because we're looking at the rate of change of the shadow with respect to time. And on the other side, I'm going to have 6 dx dt. Why dx dt? Again, I'm looking at how quickly Santa's walking towards the light as opposed to time. Not as opposed to time, but over time. So I know dx dt. Dx dt is negative 5. Dz dt then remains the only variable I don't know. So I have 10 dz dt equals 6 times negative 5. And that's going to be 10 dz dt equals negative 30. So dz dt equals negative 3 feet per second. I hope you can see that on there. The rates, the units on this guy, dz dt is negative 3 feet per second. So there's I just worked out for you several different related rate problems. They're all unique. So if there's one that you would like to see, or I can take a stab at, or maybe I could get you going in the right direction, just tweet at Hazelwood Math, and I would love to be able to help you with that. These can be a little bit tricky until you figure out what's going on, but they're so cool. They really are neat and fun, and once you put Santa in anything, I mean, how can you say no? So anyway, that's it for this section. And again, practice this problem, cover it up, try it again. Can you work it out on your own or not? And if you can't, come back to the video, see where you're stuck, and then take the next step and try again.